Last week we talked about non-repairable systems. Reliability has to do with how long is a product going to perform whatever its designated design duties are. And when it breaks, that's generally considered a bad thing, of course. Sometimes things break and we don't repair them, we throw them away, like a light bulb. If a light bulb burns out, we throw it away and we get a new light bulb. That would be considered a non-repairable system. This week, we're going to talk about repairable systems. So you've got a system, say your car, for example. When something breaks on your car, obviously you don't throw it away. Well, I've owned a couple of cars where maybe you would, but normally you would not throw your car away, you would get it repaired. And so we're interested in analyzing that repair rate, if you will, where the car runs for a little while, it breaks, we repair it, we put it back in service, it's performing its duties again, and it runs some period of time longer, and then it breaks again, so forth and so on. Those are repairable systems. Generally, you're going to find that repairable systems, not always, but generally, they're more expensive systems where you can afford to do the repairs rather than throw them away. So that's what we're talking about today. Cars, HVAC systems, how much we might spend over life to fix these things. So generally, that falls under this area called recurrence analysis. And we're going to spend most of our 30 minutes today talking about that. I'll also touch on reliability growth and reliability forecast. And then we'll also touch here on repairable system simulation, which is a JMP Pro feature. So here's recurrence analysis. Let's see, I think we've talked about most of this. Repairable systems are repaired and placed back into service. So we're looking at serial failures. So we can examine mean time between failures, for instance. A lot of people refer to mean time between failures. We're going to talk about that a little later. That mean time between failure can be misleading. So we want to be careful about that. We might want to know which system is more reliable than another system, and so forth. So let's talk about this computer board failure problem. So here's our data set. I got this from a JMP Discovery Summit talk that was given by David Trindade back in 2015. And you can get to these Discovery Summit talks on the website. Some of them are even recorded. This one happened to have just the PowerPoint file in it. We've got one computer that we're analyzing. At various points, these are days of operation, this computer needed a repair. At 108 days, one of the cards inside the computer failed, and it was repaired. Then at 178 days total, cumulative, we had to make another repair on that board. We've replaced the board again. And at 273, we replaced it again and on out here. And our study ended at 1,000 days, where it was still running at 1,000 days. Now, one thing that you might be tempted to do in this case is use the tools that we looked at last week, life distribution in particular. And if we do that, we could look at the life of the board before it failed. So here's 108 days, which is the first board, and then 70 days is 178 minus 108. So all I've done is just taken the delta between the time of failure. And then out here, we've got, were these censored or not? And remember, censored meant it was still running at the end of the test. Well, the first one lasted 108 days and it broke, 70 days and it broke, and so forth and so on for these cards, until we get down here to the last one. It was running for 12 days and still running, so it's considered censored. So if we do like last week, we go to analyze, reliability and survival, and life distribution. We say the life of the board, this might be what we're tempted to do. We say the life of the board is that, sensor is this. and we say okay, we get this output where we get to see these are the failure times of the boards and the probability of failure. And we can jump into doing fit all distributions on this data. And it comes up and tells us that the Weibull distribution is the best fit. Well, that's fine. It looks like it does indeed fit that straight line pretty well. Without rehashing too much from last week, let's just jump down here to the hazard profiler. And what it shows us is that the hazard profiler is kind of the instantaneous failure rate. And from this plot, it would appear that we have very few failures early in these intervals, but then the failure rate increases as we go up in life. So if that interval is out here towards 150 days, we have a higher failure rate. Okay, keep that in mind. That's if we analyzed it with last week's reliability tools. This week, what we're going to do is analyze reliability and survival, and we're going to do recurrence analysis. With recurrence analysis, we need to tell JMP what's the event timestamp, and for that, we're going to use this cumulative column. So we're going to say that's the computer age. We have to give it a label, even though we've only got one computer that we're studying here. JMP still requires that we give it a label. And then there's this cost column. Now cost, in this case, I'm just considering it a repair. So it's this column. But if we had the actual expense to repair that board or to replace the board, whatever it might be, we could put the actual dollar numbers in here. That's what we mean by cost. For this case, it's simply repair. So I'm going to put that in here. There are some other options down here. I'll let you read about those. We don't really have time to go into those today. And what we get are these plots. This one up here, first of all, is the event plot. It simply shows every dot represents when the computer failed. So here's our 108, here's our 178, all the way across, and out here to 1,000. And if you look, that last point was 988. So that's 988, and that little red line, if you can see it, extends just a little beyond that. So this is simply a plot of our raw data. JMP always likes to look at that. This is the mean cumulative function. So this tells us when are these failures occurring over age. So this is the number of failures on this axis versus the computer age going out this way. And what we can see here is there's really no increase in the rate of failures. I could fit a straight line that would be pretty close to this stair-step function. And it's not ramping up like we saw over in the other plot. This computer, in fact, if you squint your eyes a little bit, it looks like maybe this is bending over just a little bit. Maybe the failures are even further apart as we go out in life than they were here in early life for some unknown reason. So what we saw by doing a life distribution misled us. We thought that the failures were going to increase over time. Maybe we would want to, if that were the case, maybe we would want to go investigate why are our failures increasing when really they weren't. That's why we want to use the recurrence analysis for problems such as this when we're looking at these kind of problems. In fact, we can plot the inter-arrival times by age. Inter-arrival time is simply that delta. Up here it was the 108, 70, those kind of things versus age. So let's plot that. And there must be a way to turn on a line fit here between these points. You could do it in Graph Builder if you wanted. But it looks like, in general, if we fit a best fit line to this, we would end up with something that has an increasing slope, meaning that the delta t between times is increasing with the age of the computer, which is a good thing, where it's a longer period of time between repairs. So those are all good things, and that's all in the recurrence analysis platform. Now, we often look at what's the average time between failures. So here we might say that the inter-arrival time, the average time between failures is, and I'm just eyeballing this, about 120 days between board failures. Well, that's interesting, but it's not necessarily telling the whole story. In this case, we have a short inter-arrival time or frequent repairs back here when the computer age is young, and we have longer times out here at the end. If these points are all spread out about an average, the same average time, then sure, a mean time to repair or mean time between failures is an appropriate measure. But if you see something like this where times are short and then they get long, or times are long and then they get short, then that mean time to between failures is misleading. And I found an example, this was actually in Dave Trendade's talk too, on mean time between failures. He had a paperclip example. So here are two scenarios. The first one, we take 3 paper clips and we bend them back and forth until they break. Well, the first one breaks at 6 bends back and forth. The second one breaks at 5, and the third one breaks at 7. So we do a quick mean time between failure calculation, 6 plus 5 plus 7 over 3. Our mean time between failures is 6. Now we're going to do that same test a different way. We're going to bend 100 paper clips, and we're going to bend each one of them 3 times. Out of those 100, only 2 break. So one way we could calculate mean time between failures is to take 100 clips times 3 bends divided by 2 that broke. That's 150. It turns out to be 150 bends for the average to break a paper clip. Well, that's not right. So you have to be careful if you're going to use mean time between failures. You have to be careful on the number that you're reporting and make sure it's really representative of your particular system. Okay, reliability growth. So now we're interested in, we've got a system that has some reliability, and we could measure that. Maybe we would look at that with the Recurrence platform. But we want to make a change to that system, and we want to see if the reliability in terms of that recurrence of events, does that change when we made our change? Did we actually improve anything? So here, let's see, let me clean up a little bit. So here's a second file. This one has to do with a turbine engine. And we start tracking, at the very start, we start tracking the number of days between or until repairs. So this is the age of the machine. So on the second day, we had to stop and do a fix. And on the 4th day, we had to do another fix. And on the 10th day, we had to do 2 fixes of some sort, and so forth on down the list. Out here to 100 days, this is considered the initial phase before we made any changes to the system. And then we put new parts in, maybe prototype parts that were supposed to address these issues that were causing us to make repairs. So we kind of reset the counter a little bit, not actually, but here at 100, we're going to start with a revised design phase. So we don't have any repairs at 100, that's the start. And then at 104, we had 2 repairs, and at 130 days, we had 1 repair. And then out here at 200 days, we took that prototype, we figured, yeah, I think that's doing us some good, and we implemented a production fix. So these are the real parts. So this is our final phase. So here at 200, we're doing good. We've got no fixes on day 200. At day 242, we've got 1 fix. On out here to day 450, which was the end of our test. That's our data set. So we're gonna, in this case, we're gonna go to reliability growth, reliability and survival, and down here is reliability growth. So here, now we've got several different formats. If your data does not happen to be, if you've got data like this or a problem like this, but your data is not exactly in this format, you can manipulate your data to get it into this format. But we've also got other formats that you can use to input your data. So I'm just going to show you this first one, kind of quick and easy today. The time to event is the day column. The event count is the fixes. And the design phase is the phase. And so here's our data. Let's see if we can get this side by side here so we can see the main plot. And don't forget, as anywhere else in JMP, if I want to look at, I want to single out these 2 points right here. Maybe they were outliers. They don't look like outliers, but if they were, I could just click and drag, and those 2 points are highlighted over here in the data table. If you're new to JMP, this is called dynamic linking. It's a really, really handy thing to have. Any plot, any report is linked back to its data table in that way. So here's our data. This is number of days out here to 450 versus the cumulative number of events. So these are, here's 1 event, 2 events, and then I think we had 2 fixes. So we jump up here to 4 events and so forth all the way across. And the blue lines represent the changes that we made between initial, revised, and final design phases. So now we need to fit some curves to this. So if we come up to our main red hotspot, we can fit a model. Now these models, I've got a link under model options to tell you where to go to find out more about these models. They're different. There are different assumptions in them, particularly about how the confidence intervals are going to be calculated. We've got 5 different options. So I'm going to choose, I'm just going to do them all. So that was the Crow AMSAA. This one is the Crow AMSAA with modified maximum likelihood estimate. I believe that's what that means. And it looks like the fit is, well, it's very close to the same, maybe a little different, and the confidence intervals are slightly different. Then we can turn on the fixed parameter. And again, they're almost identical, but notice that none of those 3 are fitting our data very well. So let's do, the next one is piecewise Weibull non-homogeneous Poisson process. Piecewise, that sounds kind of interesting, like maybe it's going to handle these breaks that I have in my data. And sure enough, it does. Now, I'm going to turn these others off to make it a little easier to look at. So I'll turn those first 3 that didn't fit, I'll turn those off. And now we've got a curve fit here, and a curve fit here, and a curve fit up here. And in fact, down here it says that, yep, our piecewise Weibull NHPP has the lowest AICC number, which is what we use to compare one model versus another. So we've got a low AICC, that's a good thing. And I'll just, for the grins, we'll turn this last one on here too. Basically, it's given us the same fit in each interval, but it's zeroing out our tolerance, our confidence interval at the start of each of the windows. There may be a reason you need to do that, but we're going to stick with this one. So what we can now see is that we've got different rates of failures. It looks like there's fewer failures happening in a given period of time out here than there was in our initial phase. Down here at the bottom are summaries of the models. We don't need to look at those first ones. Here is the mean time between failures. Now I know I said you don't want to report a single number. This isn't a single number. This is showing us that mean time between failures is gradually increasing in the initial phase, and then it took a step jump and is still increasing in the second phase. And then it took another step jump and is increasing further in the third phase. This is all goodness. What we've got here are longer times between failures out here in phase 3, and they even seem to be getting even longer than that as we go out in life. So that's reliability growth. Let's take a quick look at reliability forecast. Here's my widgets file. This one I need to explain just a little bit. What we're trying to do here is make an estimate on parts that have been returned to us. We want to, they've been returned under warranty, and we want to anticipate future costs. How many of these parts are going to be coming back that we need to repair in the future? How much, if a repair costs $100, how much are we going to be spending in the future over the life of the project, the life of the product? So here we've got the volume that we produce in each month. So in July of 2000, we produced 1,991 parts. In August of 2000, we produced 2,000 parts, and so forth down the list. Now, in August of 2000, we had 8 parts returned. So on these parts, maybe they're computers or something, we've got a serial number or some kind of a date code that tells us when they were manufactured. So in August, we had 8 parts returned that were produced in July. And in September, we had 9 parts returned that were produced in July and 7 parts returned that were produced in August. So that's the way this data format is. Obviously, we can't have any parts returned in August that were made in September. So everything down here in this lower half of the matrix, they're all zeros. So what we get is this kind of upper diagonal matrix. This is actually called the Nevada format because literally, believe it or not, it's in the shape, it reminded somebody of the shape of the state of Nevada in the US. So, so what you end up with is this triangular matrix of values. Again, there's other ways to input this data. This is one way that's pretty common in the industry. So how do we analyze this? Analyze, reliability, and then reliability forecast is what this is called. This is Nevada format up here. A couple of other formats if your data happens to be in a different format. We have to tell JMP what's the production count. That was our volume column. We have to tell it the timestamp, which is time. And then we have to give it the failure counts, which are all of these other columns. And we're ready to go. These first plots up here are diagnostic plots. This is simply, the first one is production count versus time. So I can look across here and make sure, using my subject matter expertise, does that look right? Have I got something typed in wrong? This one down here is the cumulative failures that we see over time. So here, if I picked on one particular month out here, this would have all the failures that we received in that particular month from all the production that happened in previous months. So it's accumulating as we get further and further out. Again, we're looking for any unusual behavior just for diagnostics. Same thing here, we should be seeing, this is for each month's production, what is its cumulative failure rate. So we should be seeing roughly parallel lines between these guys. So just some diagnostics. Let's get on down here to the bottom where we see the analysis. At the left, this is the count at risk. So this is our production rate starting in whatever our first month was, July of 2000. This was our production rate, same as this chart up here at the top. But now we're out here to current day, and we need to tell JMP, hey, we've got more production coming on this particular part. Now, you can build a data table and import it into JMP and tell JMP, this is what we actually believe is going to happen. What I'm going to do is just this kind of shorthand way and say we expect production to stay at about the same rate out to January of 2005. And at that point, our production is going to cease on this particular model. We're going to stop production on it and let it go. Over here, we get to describe our contract length. So how long is the warranty on this product? Well, let's say it's a 12-month warranty. Take it. Yeah. So anything built in July of 2000 will be out of warranty by July of 2001, and we don't have to worry about that in terms of its returns. So now we've already had this many returns. In fact, let me change this. I believe this was based on a return, a warranty period of 36 months. So let me change that. Yeah, that's going to look a little better. So we've accumulated all these failures over time up to 36 months, which is where we are today. And we're trying to anticipate, we're going to go out another year and a half in production. What do those returns look like in the future? Well, what I can do is grab this and stretch it on out here to, actually, I'm going to come out here to 2008, roughly. This is what our returns are going to look like. This is our cumulative return rate by month, our return rate by month. So here we're getting roughly 1,200 returned per month based on our production rate and our estimated failure rates. Jump's done all that in the background. After 3 years, we get to throw away, we aren't accepting any returns from back there more than 3 years ago. So things kind of flatten out. And then finally, here in 2005, we stop production. And so we still have to honor that 36-month warranty, but at least it's declining now. So this is the production, reliability forecast. And if we're interested, we can say this is the incremental counts by month. We could look at the cumulative counts. So this is how many total returns we're going to have over time. And we can even go to our red hotspot and say use failure cost. So each of these repairs costs me $150, or each of these warranty returns cost $150. Now my scale over here is in dollars, the failure cost. So I'm somewhere up near, how many zeros is that? 8 million, between 9 million and $10 million is what this whole program is going to cost me over time. This first 3 years, this is only the tip of the iceberg. I've got a lot more to spend on this particular product. So you can do what if scenarios. What if I put it out to 48 months? What if my production ramped up and then it came back down? Those are the sorts of analyses that you can do here in the reliability forecast. Okay, last thing. So let me show you the repairable system simulation. I'll reiterate, this is a JMP Pro feature. If you have standard JMP, you won't be able to get to this. If you're interested in JMP Pro, let us know and we'll certainly get you in touch with that. This is a block diagram of a car. It's simplified, but the car has an engine, it has a transmission, a battery, it's got 4 tires, it needs a spare tire, and this is a reliability diagram. So we're talking about what's the reliability of the engine, what's the reliability of the transmission, of the battery, of the tires, and so forth. And in fact, this little box right here for the engine, if I click on that, I get information over here that's been put in. So I've done a separate analysis on the engine to find out how often it fails by itself. And that turned out to be a Weibull distribution with these numeric parameters defining that distribution. And the transmission, we'd go off and do the same thing. And we've got another Weibull distribution, et cetera, all the way through for each of these boxes. Now, next to each box, we've got a little orange box and a little blue box. This little orange box is an event, which is that the engine dies. And then what do we do in response to that event is the blue box. Well, we replace the engine. That's going to take a constant amount of time, 5 days to fix. And up here, this one is every year we're going to take the car into the shop and have the engine serviced. It's going to take a quarter of a day. Let's see, that's on up here. Quarter of a day to do that, and then it's back into service. And we've done the same thing for the transmission and the battery and the tires all the way across. This is a drag and drop. You just bring the boxes down in here and plug them all in. What do we do with that? This little green button here is a play button. And when I hit that play button, what's going to happen is Jump's going to go do 100, right here, 100 simulations across 3,650 days, 10 years. And it's going to give us an estimate out of this Monte Carlo simulation. It's going to do an estimate of how much uptime, how much downtime we have of our vehicle, and what particular components have failed in that vehicle. So maybe we can go do something to improve that. So let's take a look at that. We'll hit the play button. What we get is a big, long, this has got 65,000 rows of data in it that has to do with these events, when they occur, what we do about them, how long the car was down, those kind of things. But there's also a script up here to help us understand that. Launch Repairable System Simulation Results Explorer. And that gives us these plots, and this is really what we were after. This shows us the simulation of the availability of the car. Of course, we want it to be 100% over the 10 years. This is a distribution of how much time we think this car is going to be available to us. So it looks like about 3,625 days out of the 3,650, this car will be available to drive. Down here is flipping that around. This is that 25 days, 3,650 minus 3,625. You get about 25 days of outage for this car. And then we're interested in, well, what caused this outage? Well, if I come up here to the top, I can say box plot of system total downtime by component. So here we go. Here's system downtime, and we can see at a glance that it's the tires. That in this particular car, we expect the tires to result in most of the downtime for this car. How would we improve that? Maybe you go buy better tires, although that doesn't keep you from running over nails now and then. But it looks like if you're wanting to really improve the reliability of this car, you would do that, followed by the battery and then the engine and spare and transmission.